Welcome. This video will see an example of calculating the maximum flexural stresses in beams. And we have here a beam that's supported at A and B. So we right away show the Freebody diagram. It's support at A and B. It has a cantilever part from A to the left side of it, and then there's a distributed load. There is a point force load 30 pounds at the tip of the cantilever, and there is a point moment load 50 feet pound in the middle of the simply supported span of the beam. We did the statics already of the beam in another video, and this is the outcome of it, the moment diagram. The cross-section of the beam is given as a T-section with the shown dimensions. And we need to find the maximum tension and compression normal stresses. And we call it here sigma max plus or positive and sigma max negative or minus. So because the section here is non-symmetrical, we need to evaluate, and another thing is also that there are positive and negative moments along the length of the beam. So we need to evaluate the beam sections with positive and negative bending moments, because over the section there are positive and negative normal stresses developing in each one of these sections. So we need to get kind of a big picture of what's happening and what type of stress is developing at different possible critical sections. And then kind of once I have this big picture, I can really know where is exactly the maximum positive and negative normal stresses developing at which point and at which section. So if we look, we know from the bending diagram we have two critical sections. The positive moment maximum one is 1003 at point C here. I'm calling it point C. And the maximum negative moment, MA, of 300 foot-pounds. And let's see what type of, or what's the distribution of normal stresses at each section. So if I'm drawing for section A, and it's a negative moment, which means that it's from the negative moment definition, it's the one causes negative stresses or, at the bottom of the beam, and positive stresses or elongation of the section at the top of the beam. So you see at the top, this bold line is kind of tilted to the right, and that means that the top of the beam is elongating and the bottom of the beam is compressing. Because of the bending moment. And you can see the head of the arrow of the moment is kind of compressing the beam at the bottom, and the tail of it is kind of pulling the beam in the top. So this is kind of, I'm looking sideways in that section at A. And if I try to give now titles for the maximum or notations for the maximum stresses developing in this section. So the top is a positive moment like we explained, so I will call it sigma max positive A, and the lower one is sigma max negative A. And we can see that there's, unlike symmetrical sections, the top and the bottom stresses in symmetrical sections are equal, but this is not a symmetrical section. It's a T section, so the centroid is a little to the top. So the distance to the top point of the beam is less than the distance to the bottom point of the beam. So there's less stresses developing magnitude-wise at the top part of the beam compared to the bottom. So we can see that even with the linear distribution of the normal stresses. So if we look at section C, the moment is positive, so it's causing tension at the bottom. It's larger in value, so it's 1000, it's almost 3 times or 3.5 times more than the negative moment. And it will cause here compressive stress in the top and tension stress in the bottom. And I can see here visually that like considering the magnitude of the moment and distances to the top and the bottom of the beam, fibers, the positive moment from the positive stress from the positive moment, so sigma max plus C, seems to be the largest positive moment in the whole beam. So kind of I can visually here right away calculate sigma max positive C, which will be the sigma max for the whole beam. But the sigma max negative, the negative maximum stress here is not really a clear cut because the maximum positive moment is larger, but it causes compression at the top of the beam, which has the least distance from the centroid. So it has less distance than the bottom part of the beam. And then for the other, like section A, you see that there is a negative moment. It's smaller in value, negative 300, but it has a larger leverage, you can say, arm, which is the distance from the centroid to the bottom points of the beam. So it's not a clear, visually here is not clear, or logically is not clear which one is larger, sigma max negative at C or sigma max negative at A. So generally, the process is you look for critical sections if it's non-symmetrical beam, cross-section, and you have both positive and negative moments. So it's safer to analyze both sections that have the positive maximum moment and the negative maximum moment, and analyze the maximum and negative stresses developing in each, and then kind of compare the negative stresses developing in both sections and pick the max. That will be the negative maximum stress in the whole beam, and similar process for the maximum positive stress to find for the whole beam. So we have now the process laid out, so we need just to calculate each one of these 4 stresses and then pick from each couple the maximum stress developing for each type, tension and compression. So the first thing I have to calculate is first the inertia, moment of inertia. And this section here, I'm given the centroid. It's kind of a one step that was done for us, so that's good. One thing we need to do is calculating the inertia, and we can see here that the section is kind of naturally split into 2 parts, or 2 blocks, the flange and the web. So I will calculate the inertia using the parallel axis theorem. Please review statics to follow up the calculations here, but it's basically the distance between the centroid of the flange to the centroid of the whole section is 2.15 inches minus 1 inch, which is the thickness of the flange. So this is 1.15 to the power 2, and then the 3.85 here is the difference between 7.85 inches to the centroid from the bottom, and then there is a 4 inch from here to here, which is the centroid of the web. So end up with 3.85. And at the end here, I have the moment of inertia is equal to 154 inch to the power 4. So now moving to calculating the stresses, and to calculate the stress, we know that sigma is equal to mc over I. So now I need to label my different C values. There is C top and C bottom. So the C top is 215 inches, 2.15 inches, and the C bottom is 7.85 inches. So we'll start with section A, and just remind myself that the maximum moment here is 300, and its magnitude, its absolute value, because I already know positive or negative, so I don't have to use the formula that says sigma is equal to negative my over I. I will use all absolute values now, and I already know what I'm calculating here, positive or negative stress. So now I know that the positive maximum stress in section A is developing in the top point of the beam. So I will use C top, and using this, the moment here divided by the inertia. So the stress here is equal to 50.26 psi. And then moving to the bottom part of the beam, which will have a negative stress, and it turns out to be 183.5 psi. Pay attention to the units, so the moments are in pound-feet, and Everything else is in inches, so I multiply here by 12 inches per feet. Moving to the next section, which is section C, and the absolute value of the moment is 1003, and it's a positive moment, and because it's positive, it's causing positive stress at the bottom side of the beam, so I'm using C bottom, and that gives that big stress 613.5, and it kind of complies with our visual understanding of the stress distribution. And then sigma max negative C happening at the top, so I'm using C top, and that will give 168 psi. And now we have, for the whole beam, we can kind of pin down the maximum positive stress, which is the maximum of positive happening at A and C. And we can see clearly, like even with the visual distribution of the stresses, the maximum positive stress at C is the winner here. Is the one that should be controlling my design. And the sigma max negative for the beam is maximum of the sigma max negative of at A and C. And you can see now that it was not clear even visually, and it was a tough kind of close call here between 183.5 psi for at A and 168 psi at section C. So the maximum will be the one governing my stress, my design here. So maximum stress developing, positive one developing at C, and the negative maximum normal stress is developing at section A. So that was kind of a long example, but it's actually a very cool example because it shows a general case of designing a beam. You have non-symmetrical beam, and you have both positive and negative moments along the length of the beam, and you're looking for designing with different kind of interests into, like, you really want to know maximum, differentiate between maximum and negative stresses, because probably a material will have different capacities for positive or compressive axial stress, normal stress, and tension normal stresses. So this is why kind of it's a very generic example. Of course, it will much be shorter calculations if we have a symmetrical section and we have a simply supported beam, so we have just one sign or one type of moment, either positive or negative. All right, so hopefully you had fun with this exercise or example. Take care, and I will see you in other videos.